So we're on an ongoing journey in Calculus 2. Actually, this is where the journey begins in Calculus 2, which is integral calculus and beyond. In Calculus 1, you've probably learned a little bit about integral calculus, but now we get serious. The problem with solving for integrals is it's messy and it can be very complex. I mean, I love doing derivatives, because that's a fairly deductive. You start here, and it's pretty nice, I think. Integral calculus takes more creativity. It reminds me of proofs in geometry. You have to kind of figure stuff out, and sometimes you have to do tricks. And so, welcome to the first of several tricks in integral calculus, the substitution rule, where we basically take something that looks horrible and try to, substitute a few things here and there that we're allowed to do. We can't substitute anything, right? And then make it easier. So, without any further ado, the substitution rule. And this is the first one on the substitution rule on indefinite integrals. Okay, so indefinite integrals, the substitution rule. And this is 5.5 in James Stewart's calculus. I think in more than one of his calculus books, it's 5.5. But that's not important right now. So one of the key methods for solving integrals in integral calculus is called substitution. And basically what you do is you take some monstrosity of an integral and you substitute something else that makes it look much better. Now, what does that mean, Ken? Well, let's play around with it, shall we? Let's look at this little integral of mine. I'm going to let it shine. So this is the integral of 2x times the square root of 1 plus x squared dx. How are you going to integrate this thing? I mean, that looks complicated, right? Well, we have to kind of do a little guesswork here, kind of fiddling around with it. And there's several methods to fiddle around with it. So, I know that the integral of x squared is 2x. Is this a coincidence? I think not, because whoever made up this problem example, made it simpler for us to introduce the method. So, I got an x squared there, and I know that the derivative of x squared is 2x, and I've got a 2x in the equation. And I know that 1, the derivative of 1 is 0. So basically, what if, imagine, I got a good feeling about this. What if I substituted in u for 1 plus 2x? So 1 plus 2x here. What if I put u instead of that? Then I know what's the derivative of u? What is du? Well, the derivative of it is du equals 2x dx. So du dx equals 2x, right? So du, if I multiply both sides by dx, I've got du equals 2x dx, right? So the derivative of 1, as I said, is 0. The derivative of x squared is 2x dx. So basically, I've got the u for this, and then du turns out to be 2x dx. So I can, what you're saying, Ken, is that I can rewrite this as that. Because remember, we let 1 plus x squared equal u. So now I've got the square root of u, simple substitution. And then what is du? Well, du is 2x dx, and that takes care of the rest of it. Now, this is a monstrosity. But this, now there's something I can work with. So let's put it into this form. So the square root of anything is the same as that thing raised to a half power, right? So it's the integral of u to the 1/2 power du. Well, this is a simple integral of a power. I know how to do this. It's going to basically be 2/3 u to the 3/2 power. I put it on, hope you don't mind me putting it all on the same line. Just don't look at this right here. Don't look at me. Look at this right here. So the integral of a power is you add 1 to the exponent, right? So 1/2 plus 2/2 is 3/2, right? So I've simply raised it to a power. But then, so that I don't mess up the front, I put the kind of flipped version of this, the inverse of it, in front. So here's what, just to double check that this is in fact the integral of this. So if I take the derivative of this, I'm going to multiply 3/2 times the front. The 3/3, 2/2, that's going to cancel out. So it's going to, the 2/3 will cancel out if I multiply that by that. And then I subtract 1, and it's going to be u to the 1/2, which is what I started with. Ding! We have a winner here. So this is the integral. This is the integral of this. Now, let's go ahead and put the u back in, right? U was 1 plus x squared. So I take the u and I pull out the substitution, right? I go back. And so it's now 2/3 times 1 plus x squared to the third power. You can write that in a different way. You can write it as 2/3 times the square root of, actually, I made a mistake here. Let me fix it real quick. There, now we're talking. So it's to the 3/2 power. That's so to raise to the third power, that's the 3, and then taking the square root of it. So we can write it either way. Both of these are equivalent, right? We can do 1 plus x squared to the 1/2 power raised to the third power, or we can do the square root, which is the 1/2 power of 1 plus 2x raised to the third power. It's all the same thing. These are both two ways of writing the same thing. And all I've done is I've basically substituted back in, unsubstituted, the 1 plus 2x back in. And so there you have it. The substitution method has made something that looked horrible into something that was manageable. Welcome to the substitution method for solving integrals when you can. It doesn't always work. It's not always the best method, but in this particular example, it worked. And so we've seen our first example of the substitution method for indefinite integrals.